All right, hi folks, this is Larry Mussolino. I'm recording a video for Section 3.6. 3.6 deals with something called implicit differentiation. So this is going to be taking derivatives, but this is used when the function has a y embedded as part of the function itself. I'll show you what I mean by that in just a second. But I'm going to use implicit differentiation to help solve what are called related rate problems. All right, so what is this idea of differentiating implicitly? Well, let me give you an example. Let's say that we have, let me go to an example here. Let me go to this function you see on the bottom here. Notice what we'd like to do when we're taking the derivative is have y be a function of x. What that means is that we'd like to have y all by itself on one side of the equation like this, let's say. And then we've been taking derivatives of this kind of a function. But what if the function is such that you really can't solve the equation for y easily? Meaning it would be very difficult for me to rewrite this function with y by itself on one side. When that happens, notice here it says we would be hard pressed to write y explicitly in terms of x. What that really means is it would be hard to get y by itself on one side of this equation. So when we have this kind of a function, the way we're going to find derivatives is to use a method called implicit differentiation. So how will you know when to use this method? Will be for scenarios where you can't easily solve the equation for y, meaning you can't easily get y by itself on one side. Well, the basis of what we're going to be doing is really the chain rule. So when we want to calculate the derivative, we're going to use what's called implicit differentiation. Okay, so let's see what that means. All right. Now, let me jump to an example from WebAssign, and also let me explain how we're going to do this. All right, so when we have a function where you can't get y by itself on one side, we're going to still take the derivative of both sides of the equation. And what's going to happen here is anytime we take the derivative of y, because y is a function of x, of course, we're going to be using the chain rule. So what that means is if we encounter an expression involving y, we're going to have to include a y prime as part of that derivative due to the chain rule. Let me give you an example of what I mean. All right, let's take a look at this WebAssign example. So I'd like to take the derivative of this function. But to do that, I really want to notice I would try to get y by itself on one side to see if I could use our normal differentiation rules. But notice here it would not be easy to get y by itself. I'd have to take the square root and so on. So instead, I'm going to use implicit differentiation. Now, WebAssign and our textbook sometimes uses this dy dx to indicate the derivative. I'm going to use y prime. I think that's a little easier to work with y prime. But remember, y prime and dy dx are synonymous. They're exactly the same. Just different notation. So I'm going to use y prime. All right, so let's start. I'm going to take the derivative of both sides of this equation. So let me start off taking the derivative. And by the way, remember, we're taking the derivative with respect to x. All right, so let's take the derivative of 4x squared. Well, that derivative is 8x. Now, let me take the derivative of y squared. Well, the derivative of y squared would be 2y. But because I just took the derivative of y, I have to include a y prime. This is due to the chain rule. So one way you could think about implicit differentiation is anytime you take a derivative of the letter y, you're going to include a y prime term with the derivative to reflect the chain rule. All right, now let's take the derivative of 16. Remember, we're taking this with respect to x. Well, the derivative of a constant is 0, so that's going to equal 0. All right, well, my goal here is to get y prime all by itself. Remember, I want to come up with y prime equals something. So now what I'm going to do is a little bit of algebra here to get y prime by itself. So all I want to do now is a little bit of algebra work to get this y prime isolated by itself on one side. Let me subtract 8x from both sides of this equation. So when I do that, I'm going to end up with 2y times y prime equals 8x. Last step, because I want to get y prime by itself, let me divide both sides by 2y. And when I do that, I'm going to end up with y prime. I'm sorry, this should be a negative here. So now I'm dividing both sides by y prime, so it looks like y prime equals an 8 over 2 here. Simplifies just 4, so I end up with negative 4x over y. This is the derivative that we end up with by using implicit differentiation. Notice here that the derivative function includes the letter y on the right-hand side, and that's okay. So let me just work through these steps one more time. Step 1, take the derivative of both sides of the equation with respect to x. But anytime you take the derivative of y, you must include a y prime term. Then isolate y prime all by itself on one side. That's the derivative function. Okay, let's do the bottom example. Now, the bottom example is going to be a little more complicated because you might notice here in the middle I have 11xy. Well, x times y, remember y is a function of x. So really this is two functions of x being multiplied. That happens and you take the derivative, you need the product rule. So we need the product rule for this example. Okay, let me write this up here. X squared plus 11xy plus y squared equals 6. All right, I'm going to take the derivative of both sides. Now, before I do that, I know I'm going to need the product rule. And remember, the product rule says when you want to take the derivative of f times g. So remember, when you take the derivative of f times g, the way you set it up is f times g prime plus g times f prime. So let me just label. I'm going to label this 11x. I'm going to call this f. And I'm going to call this y the g function just to be able to apply the g. All right, so now let's take the derivative of both sides with respect to x. Well, the derivative of x squared is 2x. All right, now for the derivative of this 11xy, I'm going to need the product rule. All right, so the product rule says leave f alone. I'm following this product rule now. Leave f alone, so I'm just going to copy down 11x and take the derivative of g, that's g prime. The derivative of g is really taking the derivative of y. Derivative of y is just 1, but because I just took the derivative of y, I also have to include a y prime. All right, plus, now I'm taking the other part of the chain rule, that's g f prime. So the g part is y. And now for f prime, I'm taking the derivative of this 11x, that's just 11. All right, I'm almost done with the derivative. Now, let me take the derivative of y squared. Well, that's going to be 2y, but I also have to include a y prime term. All right, and let me take the derivative of the right side, but of course the derivative of 6, that's just a constant, that's 0. All right, now all I have to do is get y prime by itself. So this is really just going to be some algebra work. All right, first let me go ahead and subtract 2x and also subtract 11y from the left-hand side. What I want to do is get y prime terms isolated on one side. So I'm going to put 11x y prime plus 2y y prime on the left side of this equation. And on the right side of this equation, I'm going to move this 2x over to the other side. And I'm going to move this 11y over to the other side. So this is going to give me negative 2x minus 11y. All right, now, remember, I want to get this y prime by itself on one side. Well, y prime is showing up in both of these terms. So what I'm going to do is factor out a y prime as kind of a greatest common factor. So I'm pulling out this y prime. Let me rewrite that. I'm pulling out a y prime. And when I do that, that leaves me with 11x plus 2y. Equals this negative 2x minus 11y. Last step, if I want to get y prime by itself, I'm going to divide both sides of this equation by this quantity in the parentheses. If I divide both sides by that quantity in the parentheses, I end up with negative 2x minus 11y over 11x plus 2y. Okay, so this example was a little tricky. We had to make use of the product rule because I ended up with an x times y term to begin with. And also, remember, anytime you take the derivative of y, you have to include this y prime term. And again, that's due to the chain. All right. Folks, one application of this is solving what are called related rate problems. Related rates are really two quantities that are changing related to each other. So let me give you an example. Let's say you're blowing up a basketball. Well, as you blow up a basketball, the radius of the basketball gets bigger, but at the same time, the volume of the basketball is increasing. Let me give you another example. How about an oil tanker has an oil spill? So imagine the oil spill, and over time, let's say the oil spill is getting bigger. So here's an oil spill. Let's say it's circular, but then of course the oil spill gets bigger and bigger still. Well, think about the radius of this oil spill. Of course, over time, the radius is getting bigger as this circle expands. But at the same time, the area is getting bigger as well. So the rate of change of the area of the circle is related to the rate of change of the radius, and we can actually come up with a formula. Now, when we talk about related rates, rate means change with respect to time. So what we're going to be doing here is taking the derivative with respect to time. I want to know, how is this area increasing with respect to time? Well, that's really going to be the rate of change of area with respect to time. We're going to write that as dA over dt. What that's describing is how is the area changing over time. Of course, the area is getting bigger in this example with respect to time. I also think about how's the radius changing. Well, the radius is going to be dr dt. And again, here the radius is getting bigger over as time increases. All right, so here's the idea of setting up these problems that we're going to be looking at. All right, it says, first identify all the given quantities and then the quantity to be determined. You know, what are you being asked to solve? Make a sketch if you can. Write an equation involving the variables. So as you analyze this problem, you might end up using some formulas from geometry. For example, in that oil spill example that I just mentioned, geometry, there was a circle. So I'd have to know the formula for the area of a circle. Of course, the area of a circle is pi r squared. Then what we're going to do is differentiate both sides of the equation with respect to time. Again, the rate is how a quantity is changing with respect to time. Once you take the derivative of both sides of the equation, by the way, we're going to be doing this with implicit differentiation, you should be able to plug in known quantities to that derivative formula and also solve for any unknown quantities. Okay? So let's do some, I think the best way to see this is working through a few examples. Here's just some examples of related rates. The first one is how is velocity changing? The second one is how is volume changing? They're writing that as dV/dt. So we're going to be writing these derivatives with respect to t. Also, as we go through some of these problems, we're going to need some formulas from geometry. You probably remember some of these formulas, but here's a reminder of geometry formulas if you need this. All right, so let's jump into a few examples. Let me actually jump to a WebAssign example so that we can get started. All right, and let's try to follow the steps that were outlined on that slide for the guidelines here. All right, let's read this first one. It says the volume V of a cube with sides of length x is changing with respect to time. So these sides are getting larger of this cube. Let me draw a little cube here. So imagine I'll draw a smaller cube to begin with. But then they're telling me that over time, this cube is getting larger. So as the sides get bigger, it makes sense that the volume is getting bigger as well. All right, now it's telling me here the sides are increasing at the rate of 0.2 inches per second. Okay, and they're calling the length of the side x. Well, when I see this unit, notice the units are inches per second. So that rate of change on the side is increasing. I'm going to label that as dx dt. And they're telling us that's 0.2. Also, they're telling us that we want to know, they want to know how fast is the volume changing when the length of the side is 6 inches long. Well, that's giving us x equals 6. All right, well, what you have to do then is write an equation that relates to quantities being described in this problem. But this problem is talking about the volume of a cube that has a side x. Well, you probably remember the volume of a cube is taking the sides to the exponent 3, right? We just multiply the 3 sides together, but all the 3 sides are the same. So this would be x times x times x, which of course is just x to the 3rd. All right, now we have to take the derivative of both sides, but here's the important point. We're going to take the derivative of both sides with respect to time. All right, so let's take the derivative of v with respect to time. Well, you might remember we just talked about taking the derivative of y with respect to x. What we did is we took the derivative, but then we included a y prime term, or like a dy dx term. So when I take the derivative of v with respect to time, I'm going to do the same thing. So the derivative of v is really just 1 times dv dt. The dv dt part is due to the chain rule. All right, let me take the derivative of the right-hand side. Now, when we take the derivative of the right-hand side, remember, we're not taking the derivative with respect to x. If we were taking the derivative with respect to x, then the answer would just be 3x squared. But we're not taking the derivative with respect to x, we're taking respect to t. So when I take the derivative of y to the, excuse me, of x to the 3rd, that's going to be 3x squared. But I have to include a dx dt, again, due to the chain rule. All right, well, this is the formula that we need. So now let's go ahead and plug in. So dv dt is going to be equal to 3x squared, but in our example, we want to know how is the volume changing when x equals 6? So that's going to be 3 times 6 squared. And then I need the x dt, but that was given to me in the problem as 0.2. So now I could just multiply these numbers out. This is going to be 3 times 36 times 0.2. And when you multiply these out on your calculator, you'll get the answer 21.6 cubic inches per second. So what that's telling me is every second, the volume of this cube is getting bigger and bigger. And at this point in time, the volume is increasing 21.6 cubic inches every second. All right, let's go down to the bottom example, number 5. So number 5 says, Carlos is blowing air into a sphere at a rate of 8 cubic centimeters per second. Now, sometimes these units will help you identify what quantity is being described. When I see cubic centimeters, I know the volume measurement. Seconds is a time measurement. So really, I know this is a dV dt quantity because they're telling me how the volume, that's the cubic centimeter part, is changing with respect to time, that's the seconds part. And they told me here dV dt is 8. How fast is the radius changing when the radius is 10? So they're giving me that r, the radius, is 10. Rewrite that. So r equals 10. Really what they want me to figure out here is how fast is the radius changing? Well, that really is dr dt. So they want me to find dr dt in this example. All right, well, and by the way, it's very important to write down these quantities. dV dt equals 8 is given in the problem. R equals 10 is given in the problem. And the unknown is dr dt. All right, let's go ahead and think about the formula we need for this scenario. Well, I know they're talking about the sphere here, and we're talking about the volume. So I'm going to need a formula for the volume of a sphere. So let me jump back to that slide that had these formulas. And I'm noticing here the volume of a sphere is 4/3 pi r to the third. By the way, this slide is also included as part of the Chapter 3 summary that's posted in Canvas. All right, so I'm going to use that formula for the volume of a sphere. So let me write that out. V is 4/3 pi r to the third. All right, now implicit differentiation says take the derivative of both sides, but with respect to time. So when I take the derivative of v, that derivative is 1, but I have to include dv dt. And then on the right-hand side, 4/3 pi is just a constant, so I'm just going to copy that down. Now let me take the derivative of r to the third. Well, the derivative of r to the third is 3r squared, but I also have to include a dr dt due to the chain rule. You know, one way you can think about it is when you're taking the derivative of some variable, if it's different than the variable you're taking the derivative with respect to, you need this dr dt or dv dt. You know, if I was taking the derivative of an expression involving t, because I'm taking the derivative with respect to t, for example, let me just clarify this. If I was taking the derivative with respect to time of, let's say, 7t squared, well, because this expression involves t, I would not need the chain rule. So this answer would just be 14t. But what if I'm taking the derivative with respect to t of, let's say, I'm just going to make up a letter here, 7s squared? because this variable is different than the variable I'm taking the derivative with respect to, of course that's t, I'm going to have to include a ds dt term. So this answer would be 14s, but I would have to include a ds dt. So when the variables don't match, you need this extra term like a dr dt due to the change. All right, well, now that I have this derivative worked out, I can really plug in the information that was given. dv dt is 8. So I'm going to use that 8 here. On the right-hand side, by the way, I'm noticing this 3 in the denominator will cancel out with that 3 in the numerator. So then I'm going to end up with 4 pi. Now I have an r squared, but remember r was 10. So this is going to be 10 squared dr dt. And then, and of course, dr dt is the unknown quantity. So this would be a simple equation now I could solve for dr dt. So to calculate dr dt, of course, you'll use a calculator for this, but it would end up being 8 over 4 pi times 100. 10 squared is 100. So 4 times 100 would be 400. So 8 over 400 pi. Notice they want the answer rounded to 4 decimal places. So you would work this out on your calculator and round your answer to 4 decimal places. All right, let's go to part B of this question. I'm going to let you try part B, but I'm going to give you a starting point. Part B says, how fast is the surface area changing at that time? So at the same time, how fast is the surface area changing? All right, well, let me go back to that slide with all the geometry formulas, and I'm going to pick up the surface area formula. So I'm going to write that as, let's call it A, surface area. So I need the surface area of a sphere. Well, from that slide with the geometry formulas, the surface area of a sphere is 4 pi r squared. All right, let me take the derivative of both sides with respect to t. So this is going to be dA dt equals 4 pi is just a constant. Now I'm going to take the derivative of r squared, but with respect to t, that's going to be 2r, and I have to include a dr dt. All right, well, they want to know dA dt. Do I have everything I need to plug in here? I think I do. I know r, because r was 10. I know dr dt because I just calculated that from part A. So dr dt turned out to be 0.064, so I can plug that in, work this out on your calculator. You should get an answer that dA dt is 1.6 centimeters squared per second. So what it means is the surface area every second is getting 1.6 square centimeters larger per second. All right, let's do 1 or 2 more examples. Let me come here to this example about a coffee pot. So it says here, a coffee pot is in the form of a cylinder. The radius is 5, and it's being filled up with water. And it says the water level is rising at a rate of 0.6 inches per second. What is the rate at which the water is flowing into the coffee pot? All right, well, let me draw a little diagram here just to help us out. So they're telling us, imagine we can really just think of this coffee pot as a cylinder. So I'm going to try to draw a cylinder here. They're also telling us the radius is 5. You know, the other thing I want to do in this problem is identify what quantities are changing with respect to time. They're telling us that the radius is 5. And also we're filling this up with water. So imagine water is being put into the coffee pot, and then the height of the water is changing, right? Of course, as more volume is pumped in, the height is going to increase. So let's call this H. And of course, we're filling this up with some volume of water. All right, let me write down the given quantities here. R equals 5. By the way, notice the radius here is not going to change. You know, when you think about this coffee pot, the radius is fixed at 5. It's not like the radius is expanding over time. No, the radius is height. It's going to get bigger over time. So we know the height is changing. All right, they're telling me the water level is rising at this rate of 0.6. Well, that's really how the height is changing with respect to time. So what they're giving me here is the HDT equals 0.6. They want to know what rate is the water flowing into the coffee pot. So they're really asking me to find dV dt. All right, well, let me go back to that slide with the formulas from geometry. This is a cylinder, and we're talking here about the volume of a cylinder. If you go back to that slide, the formula for the volume of a cylinder is V equals pi r squared h. Now, the guidelines say take the derivative of both sides of this equation with respect to time. The one thing I got to keep in mind, though, is the radius is not changing with respect to time. So the radius is really fixed at 5 inches. All right, well, let's go ahead and take the derivative of both sides. The derivative of V with respect to t is dV dt. That's really the unknown quantity here. I'm going to bring down pi because that's a constant. R squared, the radius squared is really 5 squared. Now, I'm not going to include a dr dt. I'm not taking the derivative of r because it's not changing with respect to time. But I do have to include the derivative of h is 1 times dh dt. The height is changing with respect to time, so it makes sense I have to include a dh dt. The volume is changing with respect to time. Right? So I'm pouring water into this coffee pot. The volume is getting larger and larger. All right, now let's go ahead and plug in what we're given. dV dt is the unknown quantity. 5 squared is 25, so I'll just write this as 25 pi. And then dH dt was given in the problem as 0.6. And I'll just work this out on my calculator and round the answer to 1 decimal place as they're instructing. Okay, so the key part of this problem is recognizing the radius of the cylinder was not changing with respect to time, so really wanted to keep that as a constant in the formula. All right, let's do one more problem here. All right, so this one says a 13-foot ladder is leaning against this wall and it begins to slide. So when they say the ladder is sliding, what they mean here is this bottom part is going to be moving here to the left and the top part is going to be moving down. So let's call the horizontal distance x, the vertical distance y. So the rate at which the ladder moves in the horizontal distance, we can think of that as dx dt. And we'll call dy dt the change in the vertical height over time. All right, so how about if we think about writing some kind of an equation to describe the geometry of what's going on here. First, let's write down what quantities are given to us. So let me just make a little diagram here for this right triangle. You might notice this is a right triangle. So they're telling us this side is 13, This side we're going to call y, and this side we're going to call x. All right, so they want to know how fast is the top of the ladder sliding down. Well, really what they're asking us to find is dy dt. Okay, so we want to find dy dt. It says we'll know this when the bottom of the ladder is 5 feet from the wall. So what that's really telling us is x equals 5 at that point in time. So x equals 5. They're also giving us dx dt. Notice it says here the bottom of the wall is sliding at 6 feet per second. So dx dt is 6. All right, and of course we want to find dy dt. Well, when I think about the geometry of what's going on here, I notice this is a right triangle, and of course the sides are related by Pythagorean theorem. So let me write Pythagorean theorem for this triangle. It would say x squared plus y squared equals 13 squared. But, of course, 13 squared is 169. So x squared plus y squared equals 169. I actually gave that equation to you in the hint. Here the hint says, by Pythagorean theorem, x squared plus y squared equals 169. You find dy dt when x equals 5 and dx dt equals 6. All right. So what the guidelines say is write an equation, which we just did, and then take the derivative of both sides with respect to t. So let me take the derivative of x squared with respect to t. Well, the derivative of x squared is 2x, but I'm going to need a dx dt term. Now let me take the derivative of y squared. The derivative of y squared is 2y dy dt. And what about the derivative on the right-hand side of 169? Well, the derivative of a constant is 0. All right, so I have 2x dx dt plus 2y dy dt equals 0. All right, remember dy dt is the unknown quantity. So we have x equals 5. Let's plug in with what we know. All right, so this is going to be 2 times x, but we're given that x equals 5. So this is going to be 5. Dx dt, we're given the problem is 6. So dx dt is going to be 6. Plus 2y. Now we need y in this triangle. But, of course, I can figure out y because of Pythagorean theorem. When I look at this triangle, I know the one side is 5, the hypotenuse is 13. Of course, I can use Pythagorean theorem to figure out the missing side. Let's do it up here. So it's going to be x squared plus y squared equals 13 squared. X is 5, so that's going to be 25 plus y squared equals 169. I'll subtract 25 from both sides. So that means y squared equals 144. So now I know that y is 12. So y equals 12. So let me plug in y equal 12, and dy dt is unknown. So I'm just going to leave that alone. Now this is a simple equation I can solve for dy dt. Okay, on the left-hand side, 2 times 5 times 6, that's 60. And 2 times 12 is 24. So we have 60 plus 24 dy dt equals 0. And I'll subtract 60 from both sides and then divide both sides by 24. So what I'm going to end up with is dy dt equals negative 60 over 24, which turns out to be negative 2.5. The negative sign is just telling me that the ladder is moving down in the y direction. But this problem is asking me how fast is the ladder sliding down. So because they're asking me how fast is the ladder sliding down, I'm really not going to use that negative sign in my answer, because the negative sign is just telling me that the top of the ladder is moving downwards with respect to time. But because the problem is asking me already how fast is the ladder moving down, the answer is just going to be 2.5 feet per second. So every second, this ladder is falling a distance of 2.5 feet. All right, hope this is helpful as you're working in Section 3.6.